Okay, welcome to lecture, and we're going to get started with technically chapter 13. We're actually going to kind of cover a couple last things from 12 before we go to 13, but for the rest of it, it'll be mainly 13. Okay, so last time we did finish up chapter 12. Like I said, there's a couple sort of things I want to go over from chapter 12 in terms of a couple reactions, just to make sure everybody's on the same page. So this first little bit here will be from basically chapter 12, basically. So the first couple, just to make sure everybody understands sort of what happens with those reactions is, for example, if we take an aldehyde, and we do a reduction reaction with it. So remember that a reduction reaction is really when we're going to add H2 to it. Reduction. So when we add H2 to it, what essentially happens in this reaction, and again, I'll just draw H2 out like that, if you will. So we have our aldehyde. So when we have an aldehyde and we do sort of a reduction reaction of an aldehyde, again, it is just the one place on the molecule that basically is involved. And it's always in this type of reaction, a reduction of an aldehyde, it's always where the carbon-oxygen double bond. And basically what we're going to do here is add a hydrogen in. And like we talked about before, we really don't have room to add the hydrogen in with that double bond there. So what happens is, much like what we've seen with double bonds before, and we want to do an addition reaction, everything's going to be exactly the same, except that we are going to make that double bond into a single bond. So almost like what we talked about with alkanes, we're going to make that double bond into a single bond, but instead of between two carbons, it's actually going to be between the carbon and the oxygen here. And what that's going to do is allow room for each of these hydrogens to basically be added on. So one hydrogen will end up over here at the oxygen, and one will end up over here at the carbon. So if you take an aldehyde and you add H2 to it, which again is a reduction reaction, it's the opposite reaction of that oxidation reaction that we talked about. Basically, our carbon-carbon double bond becomes a carbon single bond, and we add an H to one and an H to the other. And that always what happens, doesn't matter how many sort of carbons you have on this side, the only part of the thing that will change will be right there where the carbon-oxygen double bond is. And you should recognize this. This makes our primary alcohol, right? And again, our primary alcohol gets oxidized to an aldehyde. The reverse of that reaction, again, is a reduction reaction where we add the H2. Now, we could also do the similar reduction reaction, but starting with a ketone, for example. And if we do this same reduction reaction with a ketone, again, adding H2, same thing's going to happen here. Again, the only part of this ketone, and again, if you have more guys on the left or to the right of that double bond, doesn't really matter. It's only going to be that part that's going to change. And what's going to happen, again, it's going to be exactly the same. The only difference is, like we kind of did above, we're just going to turn that double bond into a single bond. And again, that's going to allow now a place for one hydrogen to add to the O and one hydrogen to add to the C where the O is attached. And there we go. And again, this is our secondary alcohol. Again, this is a reduction reaction, right? Which is the opposite reaction of an oxidation reaction. So like we talked about with alcohols, primary alcohol gets oxidized to an aldehyde. But if you do the reverse reaction, the aldehyde gets reduced back to an alcohol, primary alcohol. If you oxidize a secondary alcohol, you will get a ketone. And again, if you do the reverse of that reaction, we're going to take it from a ketone back to a secondary alcohol. Both of these have basically the same thing happens. wherever that carbon-oxygen double bond, turn it into a single bond, add an H to the O, don't press down, add an H to the O there, and then add an H to the carbon. Any question on those two reactions? So I just wanted to make sure I kind of clarified those reactions. We talked a lot about sort of the oxidation reaction, but these are just as important, which is going the other way, which again are the reduction reactions. Remember, oxidation and reduction are sort of opposites of each other in these sort of reactions. There you go. And again, these are again opposite of what we talked about with the alcohol reactions. Any question on those two? Okay. And then also before we get into 13, I do want to cover two new sort of reactions that occurs with aldehydes and ketones, and some new sort of products that occur when you react an aldehyde or a ketone with an alcohol. So let's take a look at those and some of the aspects that you get with those type of reactions. And again, this sort of covers in chapter 12 stuff, so not necessarily chapter 13 just yet, but I do just want to make sure we sort of cover it. So for example, if we start with our aldehyde, and again, I'm just going to start with a simple aldehyde. It can be a more complex one. It's all pretty much the exact same reaction. So if we take an aldehyde and we add one alcohol to it, there will be a reaction that occurs. And the same reaction that occurs is very similar to what we were just talking about. In order to sort of make room for what's going to happen, it's all going to happen pretty much right here at that carbon-oxygen double bond. And as you might be able to imagine, what's going to happen is very similar. We're going to have to break that bond into a single bond to allow certain things basically to attach. And what we're attaching is this alcohol here. So we're attaching this alcohol. And this alcohol is going to come in kind of two parts. So let's talk about the two sort of parts it's going to come in as. Let's go with pink. It's going to come in with an H. It's going to be added to one side. And this oxygen carbon group here is going to be added to the other side. So always in this case, when you're adding the alcohol to the aldehyde, the H will end up over at the oxygen, and this oxygen carbon guy will end up at the carbon. And what you will get over here is you'll have that H that gets added up there, and you'll get this oxygen carbon group that's added. And again, the guys in pink over here is basically the two parts of the alcohol. So you can think of the H as H plus coming in and the OCH3 as OCH3 minus coming into the carbon. And this compound that's formed here is a special compound. It is what is known as a hemiacetal. And the major components of a hemiacetal is, let's kind of highlight it maybe in a different color, is a hemiacetal will have an OH group, it will have a hydrogen, and it'll have this oxygen carbon group here. So those are all the main parts to a hemiacetal. So if you see something where you have this carbon kind of in the middle, and it has attached to it directly an H, an oxygen carbon group, and the OH, that is what we commonly refer to as a hemiacetal. Now, this hemiacetal can continue on, and I'm just going to redraw it the same as what we got up there. And you could add another alcohol to it. Could be the same alcohol, could be a different one. It probably will be the same. And what's going to happen in this case is at this point, we actually don't have a double bond to break. So what's going to happen is we're actually going to take something off of the hemiacetal to make room for something else to come on. And what's going to come off on this second step is, grab blue, is this OH and this H will come together. So if you have OH plus H gets you H2O. So that is where water is going to come from. And we have now essentially removed that OH out of the way. And what is left to come in is that O oxygen carbon group. So what we will get is something that looks like this. And just to delineate it here. So this oxygen carbon group is what's going to come in this place, and that's going to end up right there. Yeah. And this compound where you have added the second alcohol in also has a name. It is what is known as a acetal. And the major parts of an acetal, if you have the structure given to you and you're looking at it, is it will have not one, but it will have two of these oxygen carbon groups. So it's got two of these oxygen carbon groups. Very badly written there, sorry. Try that again, carbon, there you go. And it will also have this hydrogen here, yeah, and a hydrogen. So this is a reaction that occurs when we take an aldehyde and we add one alcohol to it, we get a hemiacetal. When we take this same aldehyde, if we added two alcohols to it, it would take us all the way down here to the acetal in that particular case. Any questions on that one? So to summarize this reaction, if you take a aldehyde and you add one alcohol to it, you will get what is known as a hemiacetal that's made. If you take an aldehyde and you add two alcohols to it, you will first make a hemiacetal, and then you will end up at the acetal at the very end. So you basically will go all the way over here. And really the difference is if you added the two alcohols, basically what you would do from your original molecule is you would take your original molecule and you basically would break that double bond to a single bond, and you basically would add this part of the alcohol twice. So you would have the OCH3 and the OCH3. And again, that's basically how you could go directly from the aldehyde to the acetal by adding the two alcohols and basically just put the oxygen carbon group of the alcohol onto that carbon and making it a single bond. So that's a sort of an important reaction. You do need to be able to sort of identify a hemiacetal and an acetal. Now, this reaction also occurs with our ketones. So we just kind of show you the similarities here with our ketones. So if we started with a ketone, and again, I'm just using a simple ketone. You could do this with more carbons. Again, nothing else changes, but like we've been talking about right about there. And if we add our alcohol, I'll make a different alcohol in this case. We'll do ethanol. So we have an alcohol and we have a ketone in this case. Again, just like in the previous one, the exact same thing is going to happen, which means the double bond is going to become a single bond. So we would draw it exactly the same, just making our double bond into a single bond. And just like what we saw in the previous one, the exact same reaction is going to occur. The H is going to be added on to the top. And this oxygen carbon group, which is a little bit bigger than the last one, will end up over here at the carbon. And again, we're just going to simply put the H onto that, make an OH group, and the oxygen carbon group would go down here. This also has a special name. This is what is known as a hemiketal. So this is what is known as a hemiketal. And what makes up a hemiketal is slightly different than what makes up a hemiacetal. So when we look at a hemiketal, it has the OH group. It has the oxygen carbon group. But the difference between a hemiketal and a hemiacetal is there is no hydrogen here. So just to show you that difference when we flop back. Here, when we got to the hemiacetal, we had the hydrogen. The reason there's a hydrogen here and not in this one over here is because we started with an aldehyde, and that hydrogen is this hydrogen right here. So it stays. When we get to the ketone, there is no hydrogen here. So that ends up being no hydrogen over here attached to the carbon. So that's sort of the major difference between a hemiacetal and a hemiketal. The hemiacetal will have the hydrogen. The hemiketal will not. Just like the other one, we could take this guy and then add another alcohol to it. And again, I'll add the same alcohol here. And just like in the previous one, the exact same thing here is going to happen when we take our hemiketal and we add another alcohol to it. Again, it's going to be the OH and the H that's going to come together to make water. And again, you really can think about that sort of freeing up the hemiketal to have room for the second part of the alcohol basically to come in. And the second part of the alcohol is going to come in the exact same way as the other one did. So we would have, and again, hopefully like much of the stuff we talked about, nothing's going to change. Everything's going to look the same. The only difference is we took that OH group off, so we're going to put in its place that oxygen carbon group. So what's going to go in that place is right here. And that's going to put the OCH2CH3. This also has another name. This is what is known as a ketal. And the major parts of a ketal is 2 oxygen carbon groups that come from the alcohol. So 2 oxygen carbon groups. And also no hydrogen. And again, it's because it really started from a ketone, which is why we don't have the hydrogen involved. So just like the other one, if you start with a ketone and you add 1 alcohol, you will get a hemiketal. If you start with a ketone and you add 2 alcohols, it will take you all the way down to a ketal. You could also see that the 2 names that have the hemi in it, hemiacetal and hemiketal, those are the ones that have the OH groups. The ones that are called acetals and ketals do not have the OH group involved. Any question on these 2 sort of reactions? Again, they're aldehyde and ketones. My guess is, again, you should be able to know these reactions. You also should be able to identify something as a hemiacetal, a hemiketal, an acetal, or a ketal. And again, just to summarize that one last time, if you have a hemiacetal, you would be looking at a carbon that should contain an OH group. It should have a hydrogen, and it should have an oxygen carbon group attached. I'll just put R for the rest of the molecule. If you have an acetal, that means you've added 2 alcohols to it. So you should have a carbon that has a hydrogen has 2 oxygen carbon groups attached. And again, those oxygen carbon groups come from the alcohol. And if you have a hemiketal, which basically started from a ketone, you would have 2 R groups, which again are just carbon hydrogens. You'll have an OH group and 1 oxygen carbon group. And if you went all the way to the ketal, you would have 2 oxygen carbon groups. Again, no hydrogen on any of these guys on the bottom, just those oxygen carbon groups. Remember, an R is just a group of some carbon containing group, like carbons and hydrogens type groups attached. Any question on those sort of final reactions out of chapter 12 with ketones and aldehydes? Okay, so then we will get into chapter 13, which is the last organic chapter somewhere. All right, so in chapter 13, we're pretty much going to talk about all the rest of our organic guys. So that's going to be carboxylic acids and esters, or you combo that together, you get that weird name I just tried to say. Carboxylic acid and esters, and these are 2 groups that have carbon-oxygen double bonds. The carboxylic acid, as I think we've talked a little bit about, has this as its functional group, the carbon-oxygen double bond with the OH group on it. That's the carboxylic acid group right there. Esters have basically a kind of a carbon to carbon to oxygen, and then much like a ketone, instead of another carbon, it actually has an oxygen. Yeah, so usually we'll have sort of this arrangement when you look at it in terms of its functional group. It'll look just like a ketone, except that it will actually have an oxygen in its place instead of that 30 carbons in a row. This is acetic acid, which is also known as ethanoic acid, which we'll talk about how to name it in just a second, but some common names. This is methyl acetate. So this is an ester over here. We have our carbon-carbon oxygen with their double bond connected to another oxygen. Over here we have our carbon-oxygen double bond and our OH group, which is your carboxylic acid group. So carboxylic acid contains that carboxyl group, again, abbreviated in shorthand sometimes. That is what is meant when you see the COOH. That COOH is basically that group right there. When we write it, it's kind of shorthand sometimes. We're referring to that group that is bonded there. The other sort of organic guys that we have left are our nitrogen-containing guys. That's our amines and our amides. Our amines are basically nitrogen-containing groups. They're very similar to ammonia. And our amide is very similar to a carboxylic acid, except that instead of OH there, it's got a nitrogen-containing group attached there. So this is the functional group for an amide. The functional group for an amine is some type of nitrogen-containing group, like so. So let's start with carboxylic acid and go about how we name it. Oh, good talk. So the carboxylic acid will have that C double bond O OH group, and because it has this hydrogen at the end, it's always going to be at the end. So that functional group will always be at one end or the other. And much like when we have that aldehyde and that H at the end, that H cannot be in the middle. So it's always got to be at an end, one end or the other. Wherever that group is and wherever this carbon is right here, that has a carbon-oxygen double bond, that is always going to be carbon number 1. So you don't have to give the location of where that is, because that group always has to be at the end. So much like the aldehyde, because the aldehyde group always has to be at the end, You don't have to give the location where that carbon-oxygen double bond is. But importantly, that will always be, again, the carbon number 1. So if we count the longest continuous chain that has this group in it, that's 1, 2, 3, 4, 5, 6. Again, 6 based off of hexane. We're going to drop the last part of it, and how we name it is OIC acid at the end. So hexane becomes hexanoic acid for the longest carbon chain that's there. Then if we look, we have 2 groups that are attached. We have a methyl group there. We also have a methyl group over here. So just like we've done before, that is where we get our dimethyl part. Again, hexanoic acid for the 6 carbons that has a carboxylic acid group. Now, in terms of numbering, again, because this guy is going to be carbon number 1, like it shows here, this would be carbon 2, this would be carbon 3, this would be carbon 4, this would be carbon 5, and carbon 6. So the carboxylic acid group gets the priority in terms of numbering. And that, as you can see, means that we have a methyl group at carbon number 4 and a methyl group at carbon number 5. So again, putting all that together gives us 4,5-dimethyl hexanoic acid. Any questions on that name there? So just like before, because again, the carboxylic acid takes the priority, whichever way you number it to give it the smaller number, it should always be 1, by the way. It will either be on the left-hand side or the right-hand side. Everybody else obviously is numbered accordingly. Any questions on that name there? Go. So some simple carboxylic acids go by sort of their common name. This is formic acid. This is acetic acid, which is basically vinegar and so forth. But if we were to name this sort of following our rule here, this is 1 carbon, which is based off of methane. We're going to get rid of the E because we have this carboxylic acid. So its IUPAC name would be methanoic acid. So methanoic acid is the same as formic acid. And again, the OIC acid because of the carboxylic acid group. This is acetic acid. It has 1 carbon, 2 carbons, which is based off of ethane. We're going to drop the E because of the carboxylic acid group. And the IUPAC name would be ethanoic acid. So ethanoic acid is the same as the common name of acetic acid, and acetic acid is the major component in vinegar. And benzoic acid, basically we have a benzene ring with the carboxylic acid attached to it. And that again is based off obviously of benzene and our carboxylic acid group there, which is benzoic acid. So methanoic acid, same as formic acid. Ethanoic is the same as acetic acid. I will say acetic acid and ethanoic acid, you should know that they are sort of the same thing. That one, a lot of people do use their sort of common name when they are naming it. So a lot of people will kind of use acetic acid instead of ethanoic acid. Any questions on carboxylic acids? So then let's talk about how we name basically a ester. So remember, the ester has the carbon-oxygen double bond. It's got that oxygen connected to a carbon group. And basically, we name it one of 2 ways. We basically will look at it and we will find the longest carbon chain, and that will be basically the base of our name. So we got 1, 2, 3, 4, which is based off of butane. This is our ester here, our carbon oxygen double bond with our oxygen connected to another carbon. And it becomes butanoate is the way that we sort of end that. But then connected to the other side, as highlighted down here, is a group that's attached, and it's named like a group. And this again is our methyl group. So our butanoate comes from our longest chain, heading towards the carbon-oxygen double bond. And if we kind of put all of that together, we will get what is known as methyl butanoate. So methyl for the smaller part that's attached, butanoate for the longer part. Really, if you kind of break it up right about here, this part comes from an alcohol, and this part comes from a carboxylic acid. So the part that comes from the carboxylic acid gets the OH at the end of it. And the part that comes from the alcohol, you just basically name it like a group. So you kind of go to the left of the oxygen. So I'll put the box here. Kind of go to, we'll box this oxygen right here. So you go to the left of that oxygen for the longest carbon chain, or I don't want to always say the left, but you head towards the carbon-oxygen double bond, which happens to be to the left in this case, and you get that longest carbon chain. And you go to the other side where you don't have the double bond, and you'll get the group that's attached. Now, esters can form hydrogen bonds with each other because they actually have two polar groups. This is polar right here, and this is polar as well. And it can hydrogen bond, and it can actually hydrogen bond to itself, where one hydrogen here is bonding to the oxygen on that double bond. And the same thing over here, this hydrogen is bonding to the oxygen on the double bond. So carboxylic acids and esters are polar compounds, but only carboxylic acids can undergo intermolecular hydrogen bonding. Again, an ester cannot hydrogen bond with itself because, let's look at the ester, where'd it go? Right here. This ester has a carbon group here, not a hydrogen. So because the ester has a carbon group there and not the hydrogen like we see in a carboxylic acid, it is not able to hydrogen bond with itself. It can hydrogen bond with something else, but it cannot do the hydrogen bonding, if you will, because it doesn't have that hydrogen that's there. So a carboxylic acid, which does have that hydrogen in that place, is able to do hydrogen bonding with itself and other things as well. Now, because carboxylic acid could double hydrogen bond, that means that this is actually something that has a higher boiling point than sort of our winning guy so far, which has been alcohols. So carboxylic acid actually will have a higher boiling point than an alcohol, because an alcohol only has this group. So although it can hydrogen bond, cannot also hydrogen bond with itself at this location, like in a carboxylic acid. So actually our carboxylic acid will have the highest boiling point, finally something that will beat an alcohol. A carboxylic acid obviously will obviously have a higher boiling point than a ester, which is this guy right here. And if we were to name sort of the real name of it, this is a common name, so we'll just cross it out for our purposes. If we go to our oxygen, where our carbon is, and again, if we go towards the side where the double bond is, that's going to give us the base of the name, which is 1 and 2 carbons. So 2 carbons is based off of ethane. So this would be ethanoate. And if we go the other way, this is from the alcohol, we would name it as a group, and this would be known as methyl ethanoate, the IUPAC way of naming it. Again, what I crossed out is more of a common name. And again, if we kind of look over here, this is our propanoic acid. Again, 1, 2, and 3 based off of propane. We're going to drop the E because of the carboxylic acid group. and it becomes propanoic acid, which is the name that we see there. Any questions on that? So as I mentioned before, finally, after looking at everything where alcohols always sort of have the higher boiling point, we finally have something that could kind of beat an alcohol in terms of that. And it's really because of the carboxylic acid's ability to basically hydrogen bond in two places. And that is sometimes what it refers to as they can make what is known as a dimer, which is basically two carboxylic acids hydrogen bonding, much like what we saw in the previous picture. Like so. Again, hydrogen bonding like that, making a dimer basically. Remember, as we get something that has the ability to hydrogen bond, and something like carboxylic acid that can kind of double hydrogen bond, that's going to increase things like boiling points and melting points when we're trying to compare them. Now, some simple carboxylic acids, formic acid, which again is methanoic acid, acetic acid, which is ethanoic acid, again is, for example, the biggest part of vinegar is basically acetic acid. Now, sometimes with carboxylic acids, several skin products are what is known as alpha hydroxy acids. And what that means is when you look at the carbon-oxygen double bond, the carbon right next to it is what is sometimes referred to as the alpha carbon. And that's why it's known as an alpha hydroxy acid. Hydroxy acid because of the OH group that's attached there. By the way, if you move 2 carbons down the road from that, that is what is known as the beta carbon as well. So we'll see that a little bit more, I think, in a later chapter, the alpha carbon, the beta carbon. But that's, again, where the name alpha hydroxy acids come from. It's really a carboxylic acid that has a hydroxy group, an OH group on that alpha carbon. Some aspirin and some pain relievers also have our carboxylic acid groups. Again, this is a very common way that sometimes it is written in formulas to save space, but a reminder, when you do see that, that refers to the functional group for carboxylic acid, which is this guy here. So that's your functional group right there. Ibuprofen as well, you can see the carboxyl group, carboxylic acid group that's attached there as well. All right. So, how sort of pain relievers work is, if you hit your thumb with a nail, for example, or a hammer, maybe not a nail, that'd be bad, or a hammer would be just as bad as well. We oftentimes will release prostaglandins, and that it produces pain and so forth. When we take an aspirin or something like that, it basically blocks the production of those prostaglandins, and we sort of feel a little bit better for taking, say, a Tylenol or an Advil. And we shouldn't hit our thumb probably with a hammer, for example. So let's talk about a reaction that carboxylic acids undergo. Because they're an acid, hence the name carboxylic acid, they basically can do an acid-base reaction like we talked about. And if you remember, an acid is a proton donor, right? And a base is a proton acceptor. So if you take a carboxylic acid and water, the water would act as the base. Obviously, the carboxylic acid would act as the acid. Basically, our H is going to be donated over here. And that is where we get our hydronium ion, like we saw when we talked about acids and bases. And that's basically the water that accepted the H+, and that is our acid conjugate base pair, our base and conjugate acid pair. And when this guy loses the hydrogen as it comes off, it becomes negatively charged. So if you remember when we're doing those kind of acid conjugate base pairs, right, the charge change, because again, it's not just an H that's coming off, but it is an H+ that's coming off. So it will have an effect on the overall charge, as we see here. And that's what is sometimes referred to as a carboxylate ion. We don't have to worry about naming those or anything like that, but a carboxylic acid essentially can undergo a kind of normal, if you will, acid-base reaction, where again, it would be donating that H plus from that OH group. It could also do, again, a more traditional acid-base reaction. And when the same thing is going to happen here, we're going to have our H and our OH come together, and that is what's going to make our water. And what's left, just like before, when that H comes off, we will have our negative ion. And we also have that sodium over here. So that sodium will come together. And this is very much like what we talked about with acid and bases. An acid plus a base makes a salt, which is sort of what this is, and water, right? So it's kind of your kind of basic acid-base reaction that these carboxylic acids can also undergo. Any questions on that there so far? All right, let's see here. Let's see here. What we got? So again, here's just another example. Our H and our OH is going to come together from our base and make water. And then again, we'll get the salt. By the way, as you can see here, absolutely nothing changes from this part. And this part, it's identically the same. The only difference, it becomes negatively charged because it lost the H plus, and then we'll have that salt part that's there. Now, soap is basically salts of carboxylic acids. So they have really a long chain of carbons and hydrogens, and carbons and hydrogens are essentially nonpolar. And the front part, though, of a salt is also polar. So it's a soap, by the way, again, if you just try and draw it organically, just a long chains of carbons and hydrogens. And then at the end, it has this carboxylic acid group that has lost the H. So this part, which is line structure, all carbons and hydrogens, is what is sometimes referred to as the nonpolar tail of soap. This part over here, which does have a charge, is what is sometimes referred to as the polar head of soap. And that makes soap really effective in sort of cleaning, because most dirt is nonpolar. So when you have dirt and you put soap on, the nonpolar part of the soap, which is just the squiggly carbons and hydrogens, very badly squiggled. We'll draw this one maybe a little better. So the nonpolar side of soap, which again is this part here, the nonpolar tail, basically will surround the dirt and trap it inside. And that leaves on the outside, basically, of this sort of what is referred to as a micelle. On the outside is the polar side of soap, which is really good, because when you typically put soap on, the next thing you do is wash it off with water, which is polar. So the water is attracted to the polar side of soap. The dirt, which is nonpolar, is attracted to the nonpolar side of soap. Remember the idea of like dissolves like. So polar and polar things are soluble in each other. Nonpolar things are soluble in each other. So basically, the soap traps the dirt inside, lines itself up so all the water-loving part is on the outside. So when you wash your hands, for example, the water will take the soap away, which has now trapped the dirt, and obviously you're clean in that case. Yeah? Here's a much prettier picture of what I drew, but again, this soap is really just a long chain of carbons and hydrogen, and again, this is the nonpolar part here that's attracted to basically the dirt. Over here where we have sort of the charged part and the carboxylic acid sort of part, we have the polar part, which is attracted to water. And again, all the dirt gets trapped back here. This part that likes water gets washed away with the water, but because the nonpolar part trapped the dirt, everything goes out. Here's a 3D picture of that. Basically, again, on the outside, it's all the polar part, which is the green. All the squiggly brown part is the nonpolar part, which likes the dirt, which is all this stuff here in the middle. And again, when we wash it away, everything goes out kind of with the wash water, if you will. Any questions on that there? A much better picture of that. All right, so let us talk about some reactions that occur with esters and carboxylic acids. So the first type of reaction is carboxylic acid and esters will undergo a substitution reaction. And in a substitution reaction, if you remember, one thing goes off, the other guy goes on. So here again, Z is going to go off and Y is going to go on in its place. And that'll be your kind of typical substitution reaction that occurs. We're going to see some examples of that here, I think. So if this is a carboxylic acid that reacts with an alcohol, it is how we basically can form an ester. And an ester is formed through a process which is known as an esterification reaction. The fancy word for making an ester. And really the basic thing that happens is essentially the OH, if you want to think about it that way, from the carboxylic acid and the H from the alcohol will come together to make water, which is over here. And then what is left is essentially you just squish the two parts together. So you just squish whatever's left after you take the water out, squish it together, and you will get basically an ester. So if we look at one here, over here again is our 2 carbons, which is really ethanoic acid, which is acetic acid. And this is our 1,2 alcohols, which is our ethanol. So exactly what's going to happen here is we're going to take out water just like that. So out goes water, which is how we get it over here. And then literally what you should do is just start to the left and right to the right. So you have a CH3, you have a carbon-oxygen double bond. That is all of this. Nothing has changed. Then we would pick up over here where we left off, and we would have our O carbon, which are 2 hydrogens, our carbon with our 3, and we would have just formed our ester. So in an esterification reaction, if you take a carboxylic acid and you add it to an alcohol, you will get an ester that is formed plus some water. And basically all you have to do is take out water, and that is the OH from the carboxylic acid and the H from the alcohol. And then basically whatever's left on the left-hand side, whatever's left on the right-hand side, you draw exactly what you have there, and you basically just squish these 2 parts together, and you put these 2 parts together. So you do need to know this reaction. Esters have a lot of smells associated with them, and they're made by taking a carboxylic acid and an alcohol, taking out water, and basically squishing everything together. Any questions on that reaction there? So let me see here. we'll talk about these, and we'll go back and do that then, I guess. So let's talk about another sort of reaction that occurs, and this is what is known as a hydrolysis reaction. So hydrolysis is basically when we add water, and an ester hydrolysis is basically the opposite of an esterification reaction. So in an esterification reaction, we start with a carboxylic acid. And we take an alcohol and we get an ester. In a hydrolysis reaction, we start with an ester, and we add water. And we actually, in certain cases, can go back to the carboxylic acid plus an alcohol. Or in other cases, we may not actually get back to the carboxylic acid, depending on the type of hydrolysis reaction. So this is sort of the reverse of the esterification reaction. It's basically breaking the ester back into its parts. So this reaction, and this is what is sometimes referred to as an acid hydrolysis, because that is why we have our sulfuric acid here. So this is an acid hydrolysis. Again, the acid here is a catalyst, so it is not basically doing anything. And really what's going to happen in this case is just like this. You can imagine when we make the ester, we put them together right here, and that's where it breaks apart. Yeah. And basically, you could draw the two parts of it. And then the other part. And then this guy comes on just like so. So we're going to put an H back onto here to get us to an alcohol. And to get this one to a carboxylic acid, we need to put the OH on. And again, that comes from water, basically. So water, this hydrolysis reaction is basically the reverse of that esterification reaction. We're going to take an ester and get back our carboxylic acid and our alcohol. By the way, if we name this here, this is 2 carbons from the carboxylic acid side. So that is what is known as ethanoate. And coming the other way here, we have an ethyl group. So this is ethyl ethanoate. If we name this guy, this again is 1 and 2 carbons, and this carboxylic acid, this would be ethanoic acid. And that is again ethanol here, by the way. So you want to remember how to name these guys as well as we come across them. And I think we might have a base hydrolysis. No. So we just have that one here. And we will see this guy here in a later chapter as well. This is a triacylglycerol, and it's basically an ester bond. And here's our ester bond right here. We have our carbon-oxygen double bond with our O, and we actually have 3 of them there, which is all ester bonds. And these are found in lipids. So when we get to that chapter that we talk about lipids, we will see these guys again. So what I think I want to do is just give you some practice to make sure you can name these guys and all that kind of stuff. So I'm going to roll. It's like the lecture in reverse. It's not bad. Let's see here. There we go. I got some space, I think. There you go. Perfect. All right, so let's take a look at, again, just some of these reactions, just to make sure you could draw the products, you can name these things and all this good stuff. So let me think about here. Let me give you some to kind of work on. So let's say we took So why don't you draw the product of that reaction? Why don't you draw the product of this reaction? Why don't you draw the product of this reaction? And then why don't you also give the name of this guy, give the name of this guy, give the name of this guy, and why don't you give the name of the products that you get over here? All right, so take a few minutes, kind of work through those. We're looking for the products of that reaction. We're also looking for the names of kind of everybody we've got going on there. So why don't you take 5 or so minutes there and kind of work through it, and then we'll go through it as well. I'll do it as well because I just made it up. Okay, so let us take a look and see what we got going here. So this hopefully should be a good review of everything we've been talking about here in terms of naming and also the reactions that are involved. Let's first start with the very sloppily written one on the top here. We hopefully should be able to recognize this as a carboxylic acid. Again, because of the carboxylic acid group right here, that carbon oxygen double bond with the OH. This is a alcohol. So again, when we take a carboxylic acid and an alcohol together, we're going to take the OH, if you will, from the carboxylic acid, and we're going to take the H from the alcohol, one way to remember it. And again, that is what's going to get us water that's going to be generated. Now, once we generate the water, this is going to be basically an esterification reaction, which means we're going to make an ester. And once we have it sort of arranged like this, what we want to do is basically start with our carboxylic acid part. So we're just going to copy everything the same. That's not in the box, obviously. So what we would have, if we just copy exactly what's there, we would have a CH3, we would have a CH2, we would have another CH2, we have a carbon and oxygen double bond. So that should take us all the way through to here. We obviously are going to skip what's in the box, and then we're going to pick it up with our alcohol part here, and that's what's going to make our ester linkage right there. That makes our ester here, our carbon oxygen double bond with the O there, and that makes again our ester here in this esterification reaction. Any questions on that particular one? We'll come back and name them here in just a second. Let's take a look at the next one. Next one, we see the same situation. We have a carboxylic acid. Again, from our carboxylic acid group. We have an alcohol that's here. So always when we take these two things together, and again, they may not be drawn up perfect like this, that they line up nicely. If you need to visualize it, you may want to flip your alcohol around or your carboxylic around and sort of line them up like this. Because if you do sort of line them up like this, where you can kind of just take out the water, it makes it a lot easier to sort of draw the products. So sometimes it's helpful if they're not lined up like I did here, and kind of flip them around so they do sort of line up that way that you can see the water. And we're going to do the exact same thing on this guy. We're going to start on the left and just continue down. I'm actually going to start it here because I think I'm going to run out of room if I don't. So CH3, CH2, 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 and a carbon oxygen double bond. And again, that should take us all the way to here. 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5. Did I miss one? 1, 2, 3, 4, 6. 1, 2, 3, 4, 5. I did, you see? There we go. It's a good thing we counted, I suppose. Let's try that again. I think I'm going to start it actually over a little bit more. Make a little bit more room for it. Actually, I'll just draw it down here. I have plenty of room. So I'm going to draw it down here. So we're going to go CH3. We're not going to miss one, hopefully, this time. CH2, 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 and our carbon oxygen double bond. Now we should have everything that we have there. We're then going to go over to our alcohol part and make our ester bond. And we will look something like this here. Any questions on that one there? And again, we will name it in just a second. And let's take a look at this last one. This last one, we're actually starting with an ester. And we're going to add water. So remember, water you could think of as HOH. So this is the reverse of an esterification reaction. This is a hydrolysis reaction. And when we have an ester, when we put it together right there. So when we break it apart, it will break apart right at that point. And when we do that, We're just going to do the same thing. We're going to draw each of the parts just like it is there. So CH3, CH2, CH2, and a carbon-oxygen double bond. I'll draw the other part, which is our oxygen, CH2, CH2, keep missing one, CH2, and CH3. Remember, when we break apart an ester, it is made by a carboxylic acid and an alcohol. So when we break it apart, we need to make a carboxylic acid, which means this guy gets the OH coming from here. And this guy will get an H coming from here. Yeah. And that will give us a carboxylic acid and an ester. Any question on any of those reactions there before we name everything that's on the screen? Okay. So again, esterification reaction, carboxylic acid, alcohol, take out water, squish them together, you make the ester. Hydrolysis reaction of an ester, which is adding water, usually with an acid, will get you back the carboxylic acid and the alcohol back. So let's talk about the names of these guys. So that will help us review as well. So let's start up here with our carboxylic acid. So we have 1, 2, 3, 4 carbons, which is based off of butane. Because it is a carboxylic acid, it becomes butanoic acid. Again, for the 4 carbons and the, come back, and the carboxylic acid group. And while we're here, this is 1 carbon, which is an alcohol. We hopefully should still know that this is methanol, OL. Now, when we come to our ester, again, you could always think about it kind of right about here. This is where we put it together. This is where we break it apart. The part that goes towards the carboxylic acid side, which is where the carbon oxygen is, double bond. That is basically coming from the carboxylic acid, which is the base of the name. So that is 1, 2, 3, 4 carbons, which is based off of butane, becomes butanoate. And then the part that comes from the alcohol is basically the group name. So this would be methyl butanoate. Any questions on any of those names there? Coming down to our second set of guys. Again, a carboxylic acid, 1, 2, 3, 4, 5, 6, based off of hexane, becomes hexanoic acid. Again, because it's a carboxylic acid, there's nothing else attached. This is 1, 2, 3 carbons. This is what is known as 1-propanol, which is an alcohol. By the way, that's water, just in case we forgot. Then this was our ester that we made. So again, we want to kind of break it up right about here. Go towards the carboxylic acid side, which is where we have the carbon-oxygen double bond. That's 1, 2, 3, 4, 5, 6. That is going to give us hexanoate as the base of the name. Coming the way towards the alcohol will give us our group name, and that's a 2-carbon group. So that is going to be ethyl hexanoate. Any questions on that name there? And looking at our last guy there, again, coming towards the carboxylic acid side, we have 1, 2, 3, 4. That's based off of butane. So that's going to be butanoate. Coming the other way, which is our alcohol, we have a 1, 2, 3, 4 group. So that's going to be butyl butanoate. And that lastly here comes from 1, 2, 3, 4 carbons, which is going to be butanoic acid. And 1, 2, 3, 4 carbons, which is 1 butanol, and alcohol. Any questions on any of these names, any of these reactions that we talked about? You obviously need to be able to draw all those things and obviously give the names. Any questions? Okay, let's see here. It's probably a good stopping place for today. We're pretty much almost done with chapter 13. We have just two more types of, we get two more types of organic guys to talk about, which is our nitrogen containing guys, our amines and our amides. So we will talk about that on Wednesday. We will also roll into carbohydrates, and I'll answer your question when I get a second, okay? And we will roll into chapter 14, which should be carbohydrates, and continue on. So I think on Wednesday we will continue through here, finish chapter 13. We'll go through 14, and I may also double lecture as well. So just much like I did last time, after we're done with lecture on Wednesday during discussion, I think I will probably lecture a little bit just to keep us on track, as we are down to 2 weeks in a final, if I'm not mistaken. A reminder that our exam has been moved, obviously not on today. All right, so it'll be next Monday. So we'll take that during our normal sort of lecture time, and it will cover chapter 8, which is acid and bases. It will also cover chapters 10, 11, and 12. So I decided to take out chapter 13. So chapter 13 will not be on it. But the stuff that we did talk about at the very beginning here today, which is technically part of chapter 12, will be possibly on it. So the things about the aldehyde and ketone reactions, the hemiacetal, the hemiketal, the ketal, that stuff was technically sort of chapter 12, so that will be on it. But everything officially from chapter 13, which is carboxylic acids, esters, amines, and amides, will not be on the third exam. So technically we'll cover chapter 8, 10, 11, and 12, and we'll take that next Monday. We will wrap up chapter 13 on Wednesday lecture. We will roll into 14 and hopefully finish most of 14 on Wednesday as well. And that leaves us, one lecture and 2 chapters, which should be perfect, I think. That's how it always actually ends up in person as well, just so you know. So it will all work out. Again, the last 3 chapters, which is proteins, carbohydrates, and lipids, I think. We'll go over parts of those chapters. And again, as we go through it, I'll tell you what you definitely need to know, which pretty much means it'll probably show up on the final. So, we're not going to cover every aspect of each of those chapters. So we're just going to kind of hit some highlights from those last 3 chapters. So any questions on any of that stuff there? Okay, we'll take a little break. I'll open up for discussion in case you do have questions on something. And like I said, this Wednesday, we will finish this chapter. We will also, like I said, probably get most of, not all of chapter 14, hopefully out of the way. Yeah, so you only need to, for the exam, chapter 8, 10, 11, and 12. And then, like I said, it's the first time ever in this class I've moved off chapter 13. So chapter 13 will obviously be part of the final, but you won't have to worry about it for for exam 3. You're welcome. So obviously the homework will be due next Monday as well when we take the exam, just like we did last time. There'll be a spot for you to upload your homework. And then obviously around when lecture starts, you'll be able to take the exam. And that will leave us we really just have 2 more lectures to go. So we got this coming Wednesday and the following Wednesday as well. So I'm going to answer your question that you asked me right now. And then before you go, again, we'll take maybe a 10-15-minute break. I'll open up discussion. I think I got a message from your lab instructor, so I'm going to go post that as well in the little break time up on Canvas about what you're supposed to do for part A of the experiment. So make sure you check Canvas if you have the lab or something that you're doing for this week, because I think I just saw an email right before I got on. So I'm gonna go post that on the Canvas, and otherwise I'll see you in discussion, and then I'm gonna get to your question right now when I look at it, okay? So let's see here. Thank you very much. There's actually a correction. It's a good question. It was where did this other CH2 go to? Actually, I missed it. So there should be another CH2 there. Thank you for letting me know. It should definitely be there. So correct this, which would also obviously correct the name as well. The question was, it looks like I missed the CH2 when I was drawing it. So if we come up here, there's 1, 2, 3 carbons. So it should be CH2, CH2, and CH3. Thank you for letting me know. And then that obviously should then be propyl. Thank you. Happens sometimes. Try not to miss them. That's like second time today. So yeah, it all should definitely be there. It shouldn't have gone anywhere. So make that correction. And then, like I said, I'm going to go look and see what your lab instructor emailed me, and I'm going to post that up on Canvas. So if you're looking to do the lab or something like that, make sure you check the announcement section in about 10 minutes or so. All right, we'll take a little break. In about 10, 15 minutes, I'll open up the discussion. You can come through the discussion if you have some questions on anything. Other than that, have a good night. If I'm not going to see you later tonight, I'll see you Wednesday.